Hi, goers, welcome back. So we're going to pick up on reaction 6, which is oxymercuration, demercuration of alkenes. Okay, so this is weird. This reaction has a lot of crazy reagents that are going on, but don't freak out. It's basically the same thing that we saw before with acid catalyzed hydration. We say that up here. It's the same transformation as acid catalyzed hydration. However, we should take specific note in the fact that we do not have lack of a carbocation intermediate. Okay, we do not have a carbocation, therefore we have a lack of a carbocation intermediate, which therefore means that we cannot rearrange. Rearrangements are not possible. Okay, so let's just talk about the specific reagents that we have here. So this is mercuric acetate, HgOAC2, okay? And we have THF, which is just an inert solvent, which isn't going to really react, so don't get concerned with that. And water is going to come in and attack, and that's going to form basically our alcohol. And step 2 is sodium borohydride. Sodium borohydride is a powerful reducing agent. We don't know the mechanism yet, in Orgo 1. You'll learn it in Orgo 2. So in terms of the mechanism, you really only know up to step 1 and only part of step 1, okay? So in terms of mechanism, I'm only going to go so far, but essentially what happens is if I draw that starting material over again, okay, and this is my main reagent, we still have a concerted mechanism where that pi bond is going to grab mercury, kick off an acetate, and then also form a cyclic mercuric acetate intermediate. Okay, so what's going to result from that is this bridge. Okay, so we have that bridge, and that could have been also on a dash orientation as well. And then we have water, and that water is going to attack in the same fashion that we talked about before at the more substituted position, okay? And what's going to happen is that mercuric acetate bridge is going to break, so the resulting structure would be something that looks like this. Okay, so that acetate that we kicked off in the beginning from that concerted mechanism is used to deprotonate that proton of the water. So this is really the end product of step 1. Okay, and there is one more product, so I'll just draw both real quick. Okay, and then you also have, I guess I'll draw it down here. So these two diastereomers result from step 1. All that step 2 is going to do, and we don't know the mechanism, is it's just going to take that off. Just take it off. Okay, so it's all we need to know. So essentially, that's our products. Okay, notice how there are no possible rearrangements anywhere in that mechanism. We did not form a carbocation, so we can't do any sort of rearrangements. So it is going to follow Markovnikov's rule in the sense that we're going to form more substituted alcohols. However, if there's a potential rearrangement, that won't happen. Okay, so looking back at our starting material, we could have quickly went to the products by seeing, oh, okay, we have a secondary carbon here. Oh, we have a tertiary carbon here. Boom, alcohol on tertiary, done. That is it. So I know it looks daunting with all these reagents, but you just have to really know what's going on in terms of the specific chemical reactivity. Okay, so let's keep moving on. So in AA, that is a very characteristic molecule that I kept telling you about, on your last exam, is that if you see a pi bond adjacent to the ring, directly adjacent to the ring, and it's a 4 or 5 membered ring attached, it's probably going to undergo a ring expansion. But that only happened if we formed a carbocation intermediate. So clearly in this specific reaction, in this specific example, we are not going to have a ring expansion. We're still going to maintain the integrity of that cyclobutane ring, okay? So what results from this is essentially, so we have a tertiary carbon and we have a primary carbon, so we're going to get an alcohol on that tertiary carbon. Boom, that's my answer. Note that there is no stereochemistry indicated here because we have an achiral center. All right, and that's it for AA. Okay, so for BB, we can just quickly look here. We see that we have a tertiary carbon. We see that we have a secondary carbon. So we can imagine that we have that structure. And then we also have that structure. Okay, so I hope that helps with that one. Keep moving on. Over here, we have a tertiary. Over here, we have a secondary. So keep everything the same. So on that tertiary carbon, we had the incoming alcohol come in. Plus, we also have that. Okay, so these are the resulting structures there. All right, and I think we have one more example of that, just down here. So we have a primary position here, a tertiary position here. So essentially we know that we're going to have an alcohol form on that tertiary carbon. So we have a alcohol on the wedge and that methyl on a dash. And then we also have that. Okay? So those are, pretty easy ways to add alcohols to pi bonds without having any sort of rearrangement possible. This will be huge in synthesis, okay? So keep that in mind, okay? The next reaction also is a way to add alcohols to pi bonds, but this reaction, hydroboration oxidation, is actually going to form the anti-Markovnikov, or the less substituted alcohol. And you're like, wait, why would that do that? That's the exact opposite of Markovnikov's rule. Why would I make an alcohol on the less substituted, less stable position? Well, it has something to do with the syn addition, and it has something to do with the reagent that we're using called borane. Okay, so borane is BH3. THF is that same inert solvent, so don't bother knowing anything about that. Step 2, sodium hydroxide and this is peroxide are really involved in the mechanism for hydrolyzing and adding in that alcohol functional group. But we don't have to know that mechanism. So all you really need to know in terms of mechanism for this is that borane has this trigonal planar geometry. It is specifically going to align with that pi bond such that the BH2 fragment, so this is the BH2 fragment, this is the H fragment, it's going to align specifically where that BH2 fragment aligns on the less substituted position of the pi bond, and the H portion of that borane is going to align on the more substituted position of that pi bond. So essentially the mechanistic arrows would be something that looks like this. This pi bond going here, and that hydrogen going there. Okay, so the result from step 1 is simply this. Okay, what step 2 is going to do is going to add this source of hydroxide to where this BH2 group was and put the OH there. Okay, so in terms of mechanism, that's all we need to know what's going on. But if you look at the starting material again, we had a primary carbon. Here we had a secondary carbon. Notice how the hydroxyl group, or the alcohol, is on the primary carbon, not the secondary. Okay, and that's because of how borane aligns with our pi bond. So if we were to draw a transition state for this, that's pretty commonly asked. Essentially, the transition state would look like this. This pi bond breaks, but we form a BH2 bond there. This BH bond breaks, and that breaks there, okay? So this would be my transition state. All right, so the end product for this would just be simply that. All right, and no specific stereoisomers to consider here. All right, so let's keep moving on. So we are going down here. Okay, so again, we have a primary versus a secondary. So our alcohol is going to add on to the primary position. So no thinking. We're not playing with this phenol at all. So we really just have this. All right, and that's our major answer. All right, so keep going. We have a primary versus a tertiary. So, okay, notice that in doing such, we formed a new chiral center. It wasn't a chiral center in the sense of where our alcohol formed, but we would be expected to draw the wedge version and the dash version. Okay, so make sure you keep both of those in there. Okay, so keep going. So over here, we have a tertiary. Over here, we have a secondary. So we would expect the secondary carbon to have a new alcohol. And then, okay, so major things to consider here, okay? So remember that BH3 is going to add such that the BH2 fragment aligns on one side and the H fragment aligns on the other side. So this is something called synaddition. It's actually synaddition, or the same face. This is an anti. It's the same face alignment. So let's go back up here. The BH2 fragment and the H fragment are both going to be on both wedges or both dashes. So we didn't really see that, but both wedges or both dashes. Okay, so imagine that, let me do this over again so we can understand how I got the stereochem. Imagine that the BH2 is going to align here, and imagine that the H is going to align there. In doing such, what happens to that methyl group? By adding that hydrogen on the dash configuration, you're really putting the hydroxyl on a wedge configuration, okay? But that alcohol is going to be on the same configuration as that BH2 was, okay? So really the answer should be wedge OH plus that one, okay? So these are our major structures, okay? So over here we have tertiary, over here we have secondary. All right, and I hope that helped. All right, so the next reaction we're going to talk about is ozonolysis, and this is really neat. No mechanism again, but basically we're able to form aldehydes and ketones from our alkane starting material, and it actually cuts carbon-carbon bonds. Okay, so essentially, our main reagents here are going to be ozone and then dimethyl sulfide. Dimethyl sulfide is a reducing agent. You know, we don't really need to know anything beyond that, and no mechanism to consider. So that's awesome. So essentially what you want to do is locate your pi bond, okay? It isn't a carbonyl. So if I see a carbonyl, don't do any chemistry there. It's really just going to be carbon-carbon double bonds. Those are the pi bonds we're talking about. So the minute I see this, I'm going to draw squiggly. That tells me to cut that fragment. So we have fragment A over here. We have fragment B over here. So the resulting structure from fragment A, and I'll try and keep it in the best orientation I can. Okay, and then from B, okay. So notice this is where I cut. That was the carbon-carbon bond that I cut over here. And in place of where that carbon-carbon double bond was, I just put carbonyls. And that's it. No thinking. Okay? So you form aldehydes and ketones. You get a mixture of products here. Make sure that you include both on your test. And that's all you have to think about. Okay, so let's do this one. So essentially, I am going to draw a big squiggly here. So what I imagine happening is that there's going to be a ring opening. 1, 2, 3, 4, 5, 6, 7. Okay? So what I want to do is draw... Actually, let me draw more space over here. Okay, so this is my aldehyde. This is my ketone. So let's call that 7, 6, 5, 4, 3, 2, 1. I'll fill that all in. Okay, so where was that pi bond? So that pi bond was on carbon 2 and carbon 7. So on carbon 2 and on carbon 7, I need to have those carbonyls as well. Okay, so that's that. It cuts those carbon-carbon double bonds. So if you see any sort of cyclic system, it's going to open it up. Okay, so over here, big squiggly, your two products should be that, and it should be that. Okay, easy enough. Keep moving on. Again, if we're going to cut here, your two structures are going to be plus. And you don't have to draw these hydrogens in. Here we go. Okay, those are those structures. Okay, so again, with a ring, we know it's going to open up every time. So I find it helpful to just number the ring. Okay, so on position 2 and on position 8, oh, I'm sorry, on position 2 and on position 8, there should be carbonyls because that's where those pi bonds were. Done, no thinking. All right, that's that reaction. I like that one. Okay, reaction 9, syn-diol synthesis. Again, we don't know the full mechanism for this, but with this reaction, we use osmium tetroxide. Okay, so that's osmium tetroxide. We have water. Okay, so that's going to be our hydrolyzing agent. And then we're going to use peroxide to actually regenerate our catalyst. We actually don't know the mechanism beyond the concerted mechanism in the beginning. Okay, so let me show you what that kind of looks like. Essentially, we have this Lewis structure. You do need to know this Lewis structure. So, okay. So the mechanistic arrows are concerted in the sense that this pi bond is going to attack this oxygen, which goes over here to form a new bond there. Okay. So see these cyclic arrows? It's a pericyclic reaction, meaning it occurs in a circle. Okay. And this intermediate could have formed on the wedge configuration, so, okay, or it could have formed on the dash configuration. It wouldn't matter in this case because they have the plane of symmetry within it, but essentially you can see that this is the step that you would have to get to on a mechanism. If we were to ask, draw the cyclic osmate intermediate that results from, syn-diol synthesis, it would be this structure. And, what happens beyond that is this water molecule is really just going to hydrolyze at this position, and hydrogen peroxide is going to regenerate that osmium tetroxide. But where we cleaved, where we did hydrolysis, is where we're going to really form that alcohol. So that's all you need to know, is that we get this syn-diol. Syn meaning the same stereochemistry, diol meaning two alcohols. Okay? So that's it. It's a meso compound. All right, let's keep moving on. Okay, so essentially, since now we don't have that plane of symmetry, we're going to get two products. So we're going to get our diol here, and then we're also going to get that, syn-diol. So it's syn with respect to the diol, but remember, we're not doing any chemistry here, so leave those the way that they are. Okay, same stuff going on over here. Okay, so they can either both be on wedges or they can both be on dashes. Okay, so those are those. Okay, keep moving on. So over here, they could have both formed on wedges or they both could have formed on dashes. Okay. Pretty easy. I think you guys are getting the trend right now. So same thing over here. They both could be on wedges or they can both be on dashes. All right, now we're finally at our last reaction. So it's called catalytic reduction of alkanes. So alkanes can be reduced back to their alkanes by using hydrogen gas and these metal catalysts, these transition metal catalysts, platinum, palladium, or nickel. Okay, so it has to be platinum, palladium, or nickel. It doesn't matter which one you choose out of those three, but it has to be one of those. We do not know the reaction mechanism for this, so it's really easy to predict the products. All you have to know is that it's syn addition, okay? Syn addition of those hydrogens. So what happens here, you really won't see it in this first example, but all of those pi bonds will just go to their alkanes. Done. Okay, so then for the next example, all of those pi bonds are just going to go away. So Done. Okay. Over here, all of these pi bonds are going to go away, but it is syn addition. Okay, so this is where that consequence is going to come in. So let's just say I added 2 hydrogens on them on the dash phase. What results from that is pushing this ethyl group also on a wedge configuration. But if I wanted to put it on the, let's say they came in on wedges, that would force that ethyl group into a dash. Okay, so notice how we have to consider the stereochemistry of the substituents around the pi bond in terms of the syn addition that is happening with that reagent. Okay, so again, over here, we have syn addition. So if I had a dash hydrogen come in, that's going to form wedge methyl groups. Okay, and if I had wedge hydrogens, it would be dash methyl groups. Okay, so that's that guy. And then over here, the same thing happens. Either both these are going to become wedges, or both of them are going to become dashes. Okay, so I'm too lazy to draw that out, but I'm sure you can imagine what those two structures would look like. All right, and I think that takes us to the end of that. All right, so we're going to rank the following alkenes in order of increasing stability based on their relative heats of hydrogenation. Okay, so this is just an application, really, of this reaction above. Catalytic reduction of alkenes is how we measure, bond strength. So before in chapter 5, we were just talking about, a tetrasubstituted alkene is more stable than a trisubstituted alkene, which is more stable than a disubstituted alkene, which is, more substituted than a monosubstituted alkene, and so forth. Okay, but we didn't really know why. We were just saying because this is what happens. Well, heat of hydrogenation is the heat that comes out. So let's basically say I take alkene plus H2 is going to make alkane plus heat. Okay, this is what we're talking about. So that reaction above, we said alkene plus H2 under some sort of catalyst, I'll just say catalyst, is going to make some sort of alkane and release a whole bunch of heat. That's actually how we quantitatively measure alkene strength. Based on how much heat or how much of an exothermic reaction this is going to dictate how stable it is. Okay, so when it says rank based on heats of hydrogenation, it basically just says rank in terms of stability. So we know that a tetrasubstituted is more stable than a trisubstituted, which is more stable than a disubstituted, which is more stable than a monosubstituted alkene. Okay, so that's how I would have ranked these. Okay, so the more heat of hydrogenation means the most stable. So for tetrasubstituted would be the most stable. Okay, so keep going. So we have a trisubstituted right here, and then we have a combination of disubstituted alkenes. Okay, so we have a trans alkene, we have cis alkene, and we have geminal. Okay, so trans is the best because the steric hindrance of those substituents are 180 degrees. We know that based on our Newman projections. And then between the geminal or the geminal is the better one, the cis one, because of how close that these groups come into contact with another. These groups are pretty much farther away than these groups are over here. Okay, so that's how I'd rank those. So this is how you would basically see it predict the product section, when it encompasses multiple reactions. We only knew 2 reactions on our last exam, but now we're going to know a whole bunch. So we can subject the same starting material to a whole bunch of reagents. So quickly, let's kind of think about the major products that would follow from this. And I'm going to use the abbreviation pH for that. Okay, so essentially what happens is we're going to form a bromine halonium bridge, and then we're going to have, instead of water come in and attack, it's going to be this alcohol come into attack to form an ether. Okay, so the structure that you should have predicted for this would have been, let's say that bromine was on a wedge orientation, we would have had a bromine like this, and we would also have, if the bromine was on a dash orientation, we would have that ether come in on a wedge. Remember, it's going to attack the more substituted side, which would have been that tertiary benzylic position. Okay, so that's A. Okay, so for B, we're doing hydroboration of this starting material. So that's going to be anti-Markovnikov alcohol addition. So essentially, your structure should look like this. And remember, it was syn addition with the BH2 and the H fragment, okay? So if the H fragment, let's just do it here. If the H fragment was on a wedge, that BH2 was also on a wedge here. I'm drawing it really tiny. And here, the H group was on a wedge, so that BH2 group was on a wedge as well. Okay, that's why the stereochemical consequences happened the way that they did. Okay, so in C, you're adding hydrogen gas to the platinum, hydrogen gas and platinum to the pi bonds. Remember, that's also syn addition. Okay, so remember that it's adding a hydrogen here, and that's going to force sometimes those substituents up or down. Okay, so that's those structures. Okay, so ozonolysis is just going to cleave right here. So you're going to get a mixture of products. You're going to get this ketone, and then you're also going to get this aldehyde. All right, over here, we would get syn addition. So if I want my alcohols to come in both on wedges, they would look like that. If I want my alcohols to come in on dashes, the structure would look like that. All right. And then over here, this is back to the first exam material, but we're going to form a carbocation on that tertiary benzylic position and then add that chloride there. So that would look like this. It's really important that you guys remember your old reactions because they're definitely going to come back up on this exam. Okay. And I'm going to leave the rest of these structures and the rest of these questions for you guys to do on from the Canvas site. You guys have that answer key already published. A, B, C, and D here are just kind of pieces to what I've already talked about, and I'm going to post a supplemental video on the synthesis problems down below. So these are all mechanistic questions. You can follow those from your answer keys, but I'm definitely going to go over the synthesis questions towards the end of